Okay, great. Let me make sure. Okay, here we go. Thanks you all for having me. For those of you who don't know me, my name is Matthew DeFurio. I'm an NSF fellow at the University of Texas at Austin. Today I'm going to talk to you about the work that I've been doing as a part of a NIRCam GTO program where we identified a turnover, initial mass function in a young star forming region down to about half of a Jupiter mass. So I really appreciate all that great background from the last talk, so I don't have to give it. But essentially, for a really brief intro, stars and brown dwarfs form through the fragmentation of turbulent molecular clouds. On the left over here, I show an image from some of the simulations by Alexandra Kuznetsova, showing how you can form filamentary structures through self-gravity, where within those filaments, you can have cores that form to then produce your stars and brown dwarfs. And on the right is just kind of this cartoon schematic of this process we're talking about. Essentially, you have this molecular cloud that has turbulence, which drives overdensities and underdensities throughout the region. In these overdensities, they will continue to contract, eventually are able to collapse and form the things that we see called stars and brown dwarfs. For simplicity's sake, I'm just going to say anything that's substellar and formed through this process is a brown dwarf, but we can argue about definitions of free-floating planets and all that. Okay, so importantly, this process happens in star-forming regions and star clusters, and all of those different star-forming events will populate the galactic field. So what we see in the galaxy is really just a summation of all of these previous star formation regions, and we can use our local neighborhood to try to characterize what the products of the star formation process are as well. So some of the work that's been done recently looking at the solar neighborhood has defined the IMF down to about 10 Jupiter masses. And essentially, they just do a volume limited sample, one by my colleague at UT, William Best, and another one earlier this year by Davy Kirkpatrick. Basically, they characterize the mass function as a power law that goes down from the hydrogen burning limit to about 10 Jupiter masses with an index of about 0.6. So what that's really saying is we have an increasing number of objects as we go to lower masses. Importantly, the fragmentation process has a fundamental limit called the opacity limit, where the thermal expansion will overcome the contraction of these cores that prevents collapse, and that's what we call the opacity limit. And it's hypothesized to be around 1 to 10 Jupiter masses. This depends on metallicity, photoionizing radiation, all of these different environmental processes, but it's hypothesized somewhere around here. And so the questions that I want to address are, can we find this limit? And what is the shape of the IMF down to the Jupiter mass? So we're not sensitive to this in the solar neighborhood, but we are in star clusters. So as a part of one of the NIRCam GTO programs, we took really deep exposures just in the core of one young star-forming region, NGC 2024. It is less than 1 million years old. It's very young. It's very embedded. And the idea here is to just do really deep imaging to be sensitive down to about Jupiter mass through 30 magnitudes of visual extinction. So this is a very embedded region. We need to do these deep infrared exposures to actually be sensitive to these types of objects. Okay, so here is one of the JDBST NIRCam images. This is the F430M image, the 4.3 microns. I would love to show you this very nice color combined image, but you might have to wait a little bit to see that, maybe next month. But you can see that in these data, there's a lot of complexity. There is filamentary structure seen all over the place. There is a lot of extended emission. You see proplyds and outflows and all of that stuff. But what we're really interested here for this program is to just find the faintest point sources, just the faintest, tiniest things that we can see in these data. So, if I zoom in on one specific part of this region, you can see that nebulosity and that variable structure continues down to small scales. So when you run common point source detection techniques on these data, you get a crazy amount of false positives. These techniques are mostly designed for crowded fields and not for fields with a lot of extended emission. So it will pick up a lot of just this extended structure, some of the extension of bright PSFs, all that stuff. So we had to come up with this way in order to automate point source detection in these in regions with a lot of extended emission. So we did this really simple thing where we just made really tiny subaperture or subarrays, and we looked for deviations above the background, local background in that subarray. And we do this across the image and look for these point sources. So we just have this iterative process, and there we go. We have this faint point source in this data. And we'll do this across all of the images we have, all of the dither positions, and all of the filters. And then we will require that any detection has to have similar astrometric similar astrometric parameters throughout the dither positions and at least 2 filters to confirm that this is a true point source. And so this will get rid of a lot of the extended structure because that's not conserved across different filters. So this is the process that we went about doing. And from this, we found 100 unsaturated point sources in at least 2 filters. For this work, we just focused on the unsaturated things, a little harder to work with saturated data. And the saturated stuff will mostly be higher mass will be stars, and that's not really the focus of our work here. But this is just a color magnitude diagram. And the red line gives you a 1 million-year-old isochrone from the ATMO 2020 models. The black line is the extinction vector for this combination of color magnitude. The green lines are our saturation limits. So anything above that, we wouldn't consider in our sample. And then the black points are our data points. So you might look at this and be tempted to say, look, we found a bunch of Jupiter mass free-floating things. But we know that there can be a lot of contamination. If you look again back at this image, you can see that all of the variable structure will also produce variable extinction. So even though this region has high extinction in a lot of the region, there will also be parts that have low extinction, which allow for background stars and background galaxies to shine through and look like faint point sources. So in order to combat this, we came up with this process where we basically took a model population of the galactic field. Here we use trilegal. And we make a contour and color magnitude space based on what you would expect for typical stars and brown dwarfs that are field age. Then we take Herschel molecular hydrogen column density maps to estimate the extinction at every specific position. So on the right, I'm showing the Herschel maps where these green circles are the sources that we've identified in the data. And you can see that there are regions with really high extinction. There are regions with really pretty low extinction. So we estimate the extinction for each source and say, if this is a background object, it has to have at least this extinction. We apply that to our galactic field and extragalactic population contours. You see right here on the right. And then we compare that to the actual measured photometry of the source. From there, we can estimate the expected number of background contaminants, and that will tell us whether something's a likely member or likely a background object. So if the observed photometry overlaps this contour with the estimated extinction, probably a background object. If it's significantly further away, it's probably a cluster member. I can go into more detail if you like, but it's a little involved. So from our 100 sources, we identified 48 likely cluster members and 52 likely background objects. So on the left is that color magnitude diagram I showed you before, and this was before we did our background rejection. And on the right, this is after we do our background rejection. So you can see that most of the things that were identified as likely background objects are either very faint or pretty blue, or I guess not very red. And that would be to be expected. And you basically, a lot of these things that would be more consistent with that you might say are a Jupiter mass thing are probably background objects, unfortunately. But we want to define the mass function. So now we have our list of likely cluster members, and we can characterize the mass function in this region. We do that by we came up with this Bayesian analysis to fit a model mass function to our observed data in color magnitude space. Essentially, what we do is from the from our subarray process, we have a flux limit that we know across the entire image for every filter and every color combination. So we can define our sensitivity to sources in color magnitude space, what we see in this color map. And this basically just tells us the fraction of the image where we would be sensitive to these types of sources. Yeah, so this like purple region, we wouldn't be sensitive to any of these objects over here, but in the yellow region, we're going to recover them 100% of the time. Then we define the mass function as some functional form, for example, a power law. And we just randomly sample the power law indices. We make fake populations and then determine both whether or not we would be able to detect those objects in that fake population given our sensitivity. And then we also calculate the likelihood of that specific model given our true detections in red. So we can combine these likelihoods to get the best fit functional form to these data. And let's see, so this is my most complicated number slide. But we first start with a single power law model, and we're sensitive between about half a Jupiter mass up to 62 Jupiter masses. So that's what we're fitting over this whole time. We start with a single power law, and what we find is if we fit to these data, we have a power law index of about 0.34. I want to point out that there's a negative in the definition of this power law for, I guess, historical reasons. But this is consistent with what had been found in the galactic field population down to about 10 Jupiter masses, but our work is extending that down to about half a Jupiter mass. We then tried a bunch of different models, like a log normal or a single power law with a cutoff. We don't really find any differences with a single power law. However, when we fit a double power law model, we do find significant statistical evidence in favor of a double power law over a single power law. And what we do here is we just define the mass function as two power laws with the mass at which they differentiate to be a free parameter. Okay? So when we fit these to the data, we find that the power laws differentiate at about 12 Jupiter masses, somewhere around there. The power law index for the high mass end, so this would be roughly 12 to 62 Jupiter masses, is again consistent with what we found for the single power law in the field. However, the power law index for the low mass end, so this is half a Jupiter mass up to this breakpoint mass, is significantly different. It's -1. Now, I want to caveat this by saying our error bars are large. We don't have a large sample size. We have a pretty small sample size. So we don't have big constraints on these values. But the Bayesian evidence strongly favors this model over any of the other models we tested. And at the same time, if we look at the posterior probabilities of this low mass power law index, there's only a 10 to the -4 probability that this is similar to what we see in the field down to those 10 down to 10 Jupiter masses. So we don't know exactly how steep this low mass end would be. The error bars are large, but what we do know is that it is very likely to be different from what we find from the hydrogen burning limit down to 12 Jupiter masses. And so this would be the first identification of a turnover in the mass function in a stellar population to date. Okay, so that was our key result. And as very well said, is that we need to confirm that these things are actually cluster members. So we just have photometry. It's hard to confirm that these are members. So we were awarded cycle 3 JDBST time to follow this up with NearSpec to get prism spectroscopy of our source list. We expect to get spectra for almost all of our likely cluster members. And then we'll get spectra for about half of the things that we rejected as background objects to make sure that we were correct in doing our background rejection approach. On top of that, we're going to get near-cam parallel imaging in the edge of the cluster, which if we were unable to detect things below 3 Jupiter masses, or if there are differences as a function of environment, we should hopefully be able to see that in these near-cam images in the periphery of this cluster. Importantly, we'll be able to better estimate masses, confirm membership of these sources, and then we're also going to perform some spectral retrievals to see if we can identify any differences in the abundances, which would give us indications on the formation processes, whether these things are formed in situ or formed within a disk, accreted beyond some ice line, and then later ejected. So this is a lot of our planned work that we really need to do to confirm all of this. But with that, I guess I'm at my time, and I'll put up my summary slide, and I'm happy to take any questions.
Since you have long wavelengths also around 4 microns, you try to look for infrared excesses, because at that age, you would expect that all of these objects would have a disk, and so should have an excess. That could be helpful to confirm maybe some objects.
Yeah, this is a great question. We did try to do SED fitting to the data that had multiple band photometry. It was really difficult because you only have, maybe 5, 7 photometric points to fit an SED of a photosphere plus extinction plus a disk. There's just not enough data to actually do that well. So we didn't find a lot of evidence for infrared excess at 4.3, 4.4 microns. One thing I did was I reran our mass function fitting, assuming everything had a disk that contributed 50% of the flux at 4.3 microns. And what we find is that we have the exact same power law shape. It's just that that mass decreases from 12 Jupiter masses down to like 7 or 8 Jupiter masses. So if there is infrared excess that's contributing to the 4 micron imaging, which there will be for, especially for the higher mass brown dwarfs, maybe not so much for the 2, 3 Jupiter mass things, like that would, I don't know if that would contribute a lot. I don't think it would. I think you need 8, 10 micron imaging that would be able to identify those. But even if you take that into account, we still expect the shape of the IMF to be conserved. Yeah.
Awesome talk. Really enjoyed that. Going sort of back to QY's talk, or question for Hervé. Have you compared this to the microlensing data? Is it consistent?
No, I mean, what we were able to say is just that the microlensing work compared it to other similar populations that we compared to, and they said things were consistent. And I don't think that we have like a large enough sample size to make really definitive statements about the power law indices values. But other than that, it should be consistent with.
I mean, there's big error bars on the microlensing.
That's the
big
thing.
Error bars on this.
Yeah.
So I was wondering if those two error bars are big enough that they overlap.
Yeah, I think generally that's generally the case. We compared to what they made claims comparing to other things that we were able to definitively compare to, and they said they're consistent. So we think they're consistent at least down to 10 Jupiter masses. Not sure about down to lower masses.
So you said you found that the lowest mass is 3 Jupiter mass, right?
Roughly.
So
yeah.
can you put any upper limit below the 3 Jupiter mass rather than the 15 by the power law?
What do you mean?
Because you didn't find any object below the 3 Jupiter mass.
Correct.
So that might indicating some truncation.
Sure.
So you can put some upper limit below the mass rather than the upper for the power mass function.
Yeah, I mean, when we fit the mass function, we can add a cutoff and try to fit for what the cutoff mass would be. There's no statistical evidence that that fits better than the double power law model, again, because of small number statistics. But yeah, if we have enough things, then I would definitely do that to see if there is a true truncation somewhere.
I think just to follow up on that, can you just set a simple constraint on that mass range?
Sorry. Can you just set a simple constraint on the low mass range? Say there cannot be an abundance above X, Jupiter mass objects that are free floating, right?
Wait, what do you mean? I mean,
You do the integral. Oh,
So
Yeah.
I think that was Taka's question is can you, what is the constraint you set
Well,
for
what-
having out of your thing?
We allow it to fit down to half a Jupiter mass where we were sensitive. But we don't have enough power to actually say anything definitive about this. So we fit a double power law model across all of this. We could, if you add that cutoff, if you add that constraint where nothing can be below 3 Jupiter masses here, we don't find any better fit to the data than what we have. But we don't, again, if you look at between, right there, you don't expect very many things anyway from our estimates.
So great. So you didn't see any possible binaries.
There are definitely binaries in the data, but for 3 Jupiter mass things, we don't think there are wide companions to the 3 Jupiter mass things. But if there are, that's totally fine. I think I mentioned this yesterday. We do find, as you mentioned in the last talk, we do find binaries that are wide that have 10, 20 Jupiter masses, and that's fine. But because we're not identifying any of these things below what we expect as the limit of turbulent fragmentation, we wouldn't be able to find companions because we don't believe that they're cluster members. But there are binaries in the data for sure.